Welcome, everyone. For today's prep, we're going to introduce the idea of limits. Now, limits are ultimately going to help us define the derivative more precisely, but we're going to just kind of start by looking at what limits actually are. So first, the definition. So let's read through this, and we'll make some comments here. So we say that the number L is the limit of a function g of x as x approaches a. Now, what has to happen in order for us to say this is that g of x, the output of our function, is getting closer and closer to the number L as our input x is getting closer and closer to that number a. And the notation that we use is LIM. So the way we would read this is we would read this, the limit of function g of x as x approaches a is equal to the number L. So a way to kind of think about what the limit actually is, as input x gets close to a, and a is here as a number. It's a specific kind of place along the x-axis. So as our input x gets closer and closer to this place we're interested in, number a, the output of our function, which we'll call g of x, gets closer and closer to some number L. And that's what a limit is telling us. So it's describing what's happening to the output of our function as the input of the function kind of gets closer and closer to a specific point. So you want to think of limits almost as like describing where we're going. It's kind of like describing a place that we're headed to. All right, so I think it's helpful to look at a picture. So we're going to look at a couple graphical examples. So we'll skip past example 1. We'll come back to this in class. But I want to look at example 2. And I think for today we're going to start with these first 2 graphs and investigate these. All right. So we're going to calculate each of these limits graphically. And what we're going to do is the limit of g of x as x approaches 2. All right, so let's start with this one. This one right here. So we're interested, what's going on with our function as the input gets closer to the number 2? So first thing, we want to find 2 along the x-axis. So here's 2 along the x-axis. And, well, there's kind of 2 different directions that x can approach the number 2. We can come from the left side, or we can go from the right side. So we've got the left and the right. Okay. And now the idea with a limit is, let's start with the left-hand side. So we're going to investigate the left-hand side of our graph first. Doesn't matter. We could do the right side first. What we're going to do, though, we're going to imagine that we're on the curve here. So we're going to be a little person, and we want to think that the curve here is like a path that we're walking along. And what the limit describes is, where are we actually going? So as we walk along this curve, as x is approaching 2, we're walking along this curve, and it looks like we're getting closer and closer to this point right here. And the coordinates for that point are, the x-coordinate is 2, the y-coordinate is 1. So our left-hand limit in this case, left-hand limit, and we'll abbreviate, or the notation we're going to use for left-hand limit is x is approaching 2 with a little minus sign there. So we're a little bit smaller. All the values here are a little bit smaller than 2. So we subtract a little bit. And we're going to say that the limit here is equal to the y-coordinate of that point that we're getting closer and closer to. So in this case, it's going to be 1. So as we walk along this curve, it looks like we're getting closer and closer to that point. That looks like where we're headed to. And the value of our limit, the output of our function, looks like it's getting closer to the number 1. And we're getting the x value, the input, is getting closer to the number 2. So we've got our x-coordinate here, and then we've got our y-coordinate here. Now we can play the same game on the other side of the graph, on the right-hand side. So for the right-hand limit, the notation is very similar, but now we're using values for x that are a little bit bigger than 2. So we're adding a little bit extra to our input. All right, so now we're going to get closer to 2, but now we're going to approach it from the right-hand side. So again, we imagine walking on the curve, and we're just going to walk down the curve here, and we want to know what point does it look like we're getting closer to. Well, it looks like we're getting closer to that same point. So over on the right-hand side, our x-coordinate is getting closer to the number 2, and the y-coordinate is getting closer to the number 1. So we say that the right-hand limit would equal 1. And what happens is, because these two values are the same, it kind of looks like we're headed to the same point on either side. The left-hand limit and the right-hand limit, we're kind of getting down to the same point there. So if we put those together, we're going to have what we'll call the overall limit. So here it's just x approaching 2, and we're not specifying a direction. So it's just x is getting closer to 2. And because those values are the same, we say, well, it's equal to 1 in this case. So since the right-hand limit is equal to the left-hand limit. Okay. Let's try the next one. All right, so over here, we're interested in what's going on as we get closer to 2. So as our input values get close to 2, what's going on with our function? So there's two directions again. Our inputs can approach 2 from the left, and our inputs can approach 2 from the right. So we have kind of two sides here, just like before. All right, so let's start with our left-hand limit. So the notation again, limit of g of x as x approaches 2, but now for the left-hand limit, it's a little bit smaller, so we subtract a little bit. All right, so we want to know, where does it look? So where does it look like we're going? So we're going to imagine we're standing on the left side of our curve here, and we're just going to walk along the curve. We're going to imagine what happens as we walk along the curve and we let our x-coordinate get closer to 2. So as we walk along the left portion of our curve here, it looks like we're getting closer and closer to this point. And the coordinates for that point are 2, 1. So in this case, for our left-hand limit, our x-coordinate is getting closer to 2, and our y-coordinate is getting closer to 1. So we'd say our left-hand limit is 1. Okay, now let's try the right-hand side. So our right-hand limit, we're going to approach from the other side. So our notation for right-hand limit, limit of g of x, and x is going to approach 2 from the right. So we add a little bit extra. We're a little bit bigger. So now we're over on this side of our graph, and we're going to imagine what happens as we move closer and closer. Our input moves closer and closer to 2. So now we find our curve, and we're going to imagine walking along this curve, and we're going to see what point does it look like we approach. So as we're moving along, it looks like we're going to be walking closer and closer to this point right here. And the coordinates for that point are 2, 2. So our x-coordinate is getting closer to 2, and in this case we see that our y-coordinate is getting closer to 2. So we say that our right-hand limit is 2. And what's happening here is the left side and the right side of our graphs, they don't match up. We're kind of going in two different places. The left side wants to go one place, the right side wants to go somewhere else. And so when this happens, if we put it together for our overall limit where we don't specify a direction, so the limit as x approaches 2 in general, we're not here, these little minuses and pluses, these are kind of like directions. So we've got our left side, our right side. The overall limit, we don't specify the direction. And in this case, we would say that this limit does not exist. And the reason here is because the left-hand limit and the right-hand limit are different. Okay. So you can see, if we kind of compare these two graphs, a limit exists if the left side and the right side, it looks like they kind of match up at the same point. And a limit doesn't exist if the left side and the right side kind of look like they're going to two different places. Now, one little comment here about each of these graphs. This open dot means that that point is not actually included in our graph. So this will be something that, as we see more graph examples, it's worth noting. If we have a filled in point, that point is on the graph. Of our function. And if we have an open point like this, it's not included. It's not part of the graph. So when you see a curve like this, you almost want to think of it, it's a whole bunch of filled in points like this that are all plotted, and we've plotted so many of them that it just kind of blurs together to form a line. So all we've done is we've plotted a bunch of filled in points, and we've plotted so many of them that it just looks like a curve. And the reason why we make this point kind of a little bit bigger than the rest of the curve is just so that we notice that there's one specific point there that's actually missing on our graph. Or in this case, there's 2 points that are missing. So for the first one, it's worth mentioning that g of 2 is actually undefined. So when we look at this first graph, if we're looking at x equals 2, there's no actual filled in point along our curve there. So the only point that we have is a point that's not actually included on our graph. So that means our function is undefined at that point. But when we talk about limits, limits can still be defined, like it is here. So it doesn't matter. This point is actually missing, but as we move from the left and as we move from the right, we're getting closer and closer to that point. Similar on the next graph. So if we look at x equals directly at x equals 2, there's no filled in point. So same thing here. G of 2 also is undefined. There's no filled in point. All right. So we're going to try some more examples like this, and we'll also look at calculating limits numerically and algebraically as well. So we'll see you then. Bye-bye.